Equilibrium, a state of dynamic balance, part 1. What is equilibrium anyway? When you guys did that lab with the graduated cylinders and the straws and the water, it was super exciting, transferring water back and forth. What is it that's equal? It's certainly not the levels of the grad cylinders, but if you look closely here, the cylinder that has the higher level likely had the thinner straw in it, whereas the cylinder that had the lower level had the thicker straw. And if you were to look at the water inside each of the straws, those little volumes would have been equal. So it wasn't the level that's equal of the cylinders. As we looked here, the water levels in the cylinders were not equal when the equilibrium was established, but what was equal was the amount of water being transferred back and forth. That was the equal part. So if we imagine the equation is A going to B or B back to A, the amount going in this direction is equal going into the amount in that direction. And A and B became constant because you looked at the measurement of the cylinders weren't equal, but they became constant, unchanging. Even though you're continuously exchanging water back and forth, they were constant. So that must mean that every time you moved water back and forth, that was equal. Taking away a certain amount and adding an equal amount back. So the amount of water being transferred back and forth was equal, making the amount of liquid in each cylinder constant. So the key thing to note there, you have constant volumes, constant reactant and product, and equal amount being transferred, or equal rates back and forth. So that is equilibrium. So I mentioned here, of course, this is the same as the forward and reverse rate being equal in a chemical reaction. And when you made a graph, you may have found something that looks like this. Now, looking at the graph, we can get the same information. So it's a graph of concentration of reactants and products versus time, or in your case, it was volume of liquid versus time. And you should have seen that one curve started up high, so that was like your grad cylinder A, and grad cylinder B had nothing in it at the start, so it started off at 0. Reactants are being used up until they approach a constant amount. Products are being formed until they approach a constant amount. So this leveling off here, this plateauing, is the point in which equilibrium is established. So as time passes, and I'll have the same amount of liquid in each case. Okay? And lastly here for this video, I want to look at comparing this dynamic equilibrium to a steady state process. If we look at steady state processes, it's something that's very similar. We had a constant amount of products being formed, results in a constant product being achieved continuously, but it's in one direction. So we're making the product is remaining constant, but it is a one direction type reaction. So for example, lighting a Bunsen burner, we have a gas line coming in, a methane line, the Bunsen burner, and we have a constant flame here, but we're continuously shoving reactants in there. So that is referred to as a steady state. The equilibrium one differs from that in that it's two directions. So the dynamic equilibrium process results in a constant reactant and product being achieved due to equal forward and reverse reactions. So for example, here I have the production of ammonia, which is a spontaneous process. It naturally wants to go to the right, but when it goes to the right, it also goes back and forms reactants again. Another kind of real-life example of a dynamic equilibrium would be a bridge between two cities, let's just say. So during rush hour in the morning, we could have people from city A who work at city B and city B people working at city A. So you can see there's an equal number of people crossing the bridges at each time. And the city A population remains constant because what they're losing, they're gaining. So let's say that could be 10,000 people. City B could be 5,000 people. So these city populations aren't equal, but they remain constant because we have an equal amount of people leaving and an equal amount of people coming back. So that's kind of a real-life analogy we can use to help explain the process of
With
dynamic
destiny and
equilibrium.
Shadong, please come to